What's going on, smart people? I was recently reached out to by a graphic design tablet company known as Gaomon, who asked if I would review their Gaomon PD1560 tablet on my channel, and that makes me sound like an experimentalist when I say that out loud. But I told them, thanks for the offer, but I really don't do review videos on my channel, but I'd be happy to use it in a derivation video as opposed to using my whiteboard and maybe say some words on it towards the end of the video, and they said that would be great. So that's what we're going to be doing today. Instead of getting into a derivation on the whiteboard, we're going to be using the Gaomon PD1560. You can see for yourself if you like how it's displayed, and then stay tuned to the end of the video where I'll say some final words on it. If you want a more comprehensive review on the tablet, go check out Flammable Maths video. That's actually how I learned a lot about the tablet. And yes, I shouted you out. God, sorry. As you know, I live in Flammable Maths basement. But anyways, so today is all about Noether's theorem. You've probably heard at some point in your physics career that symmetries lead to conservation laws. We're going to be seeing for ourselves how that happens mathematically. Now we're going to be taking what's known as a covariant approach to this. All of the stuff we do will be in the language of 4 vectors and tensors and Lorentz scalars and things like that. It's because in reality that's what's more useful. You know, if we deal with conserved quantities, they should be relativistically consistent. But I understand that people aren't particularly comfortable, or not everyone is comfortable with tensors, so throughout the video we're going to be connecting the dots back to how this would be phrased in classical mechanics. That way everyone gets something out of this. And please let me know in the comments if you like videos being done like this as opposed to the whiteboard. It's definitely a hell of a lot easier to set up. But anyways, Noether's theorem. Noether's theorem. So Noether's theorem says that I don't know if there should be an apostrophe there, but I'm going to put one there anyways. It also says that for any continuous global symmetry that leads to a conservation law. And we're going to define what things like global symmetries mean in just a minute. Since I'm going to be tackling this in tensor notation and classical mechanics, I think it'll be better for everyone if we have kind of like a dictionary, so that when I write something in one notation, you know immediately how that would be translated into classical mechanics. So let's go ahead and do that. So I'm going to have 2 columns. One is going to be for classical and one is going to be for field theory. When I say classical, I mean non-relativistic. You could have classical field theory as well. But anyways, so for classical, let's go ahead and write that up here. Classical. And over here we will have field theory, FT. Okay. So the first thing is, when you want to describe the dynamics of a system, you always start with a certain formalism of describing classical physics. That could be Newton's laws, Lagrangians, or Hamiltonians. For this stuff, we're going to be looking at Lagrangians, which is the difference between a kinetic and potential term. So we're going to be dealing with Lagrangians, L. In field theory, you don't work with Lagrangians directly, you work with something that is very related, which is the Lagrangian density. And you could probably guess how those two would be related. Instead of a Lagrangian, you use a Lagrangian density, which is defined in terms of the integral d3x of the Lagrangian density. So regular L is the Lagrangian, script L is the Lagrangian density. I can almost guarantee you that you will hear me refer to script L as a Lagrangian just because I forgot to say density. But if you see me working with script L in the field theory side, I mean Lagrangian density, okay? Now, just like most things in physics, the equations that describe them, they should satisfy the principle of least action. Let's go ahead and define the action. The action is the integral over time, so dt of the Lagrangian. And if the Lagrangian is the 3-dimensional integral of the density, then we can just write this as a 4-dimensional integral. S is equal to the integral 4x of the Lagrangian density. I know people hate when I write the what you're integrating with respect to first. It's become a habit because when you're dealing with integrands that may have like 20 variables in it, it's nice to know right off the bat what you're integrating with respect to. What's a constant, what's a variable. So it just sort of happened. I'm sorry. Okay, next. In classical physics, you deal with time derivatives, and as we see these dt's in your Euler-Lagrange equations, you see ddt's, which give you the equations of motion. So you have time derivatives, d over dt. If you want to write it in the context of field theory, you replace the ddt's with what are d mu's. d mu, which is equal to the time derivative. It's a 4-vector, where the first component, or the 0th component, is a time derivative, and the 1 through 3rd component are the minus gradient. The minus comes from the metric tensor. And just like you can apply this to a scalar field, you could apply this to, say, a scalar field, which would just give you d phi over dt minus gradient of phi. It's a 4-vector, so you could take dot products with other vector, which is like a 4-dimensional analog of divergence, and so on. But yeah, so ddt's become d mu's, dt's become d4x's. That's pretty important. I'm doing all of this because just like how if you were to derive the Euler-Lagrange equations, there comes a point where you have to integrate by parts to shift derivatives around, shift the differentials, and that can be a bit confusing if you haven't done integration by parts using tensor notation before, so I think that this will be pretty useful. Okay, I gave it away up here that in field theory you use fields, go figure. In classical mechanics you'll use, generalized coordinates or their derivatives, their time derivatives to be specific. Oh, let me erase that. There we go. Okay, and so in field theory, instead of the generalized coordinates, you'll have fields which are functions of the coordinates. So we have fields and their derivatives. But again, instead of time derivatives, we have the 4 derivatives, d mu phi. Okay. And I think that's about it. That's all we'll need to connect the dots from regular classical mechanics to field theory. So I'm going to go ahead and box this in, and we will be referring to this pretty frequently. Let me also get a straight edge. That way I'm not writing at an angle. Oh, shit. I guess I can zoom out all the way. There we go. And okay. And we're also going to bracket it. Let's do over here. So we're going to split this into 2 columns where one will be in the language of tensors and stuff and one will not. So we're kind of doing it twice, but once we do it once, we can just use our little translation over here. Okay. Cool. So let's have left-hand side of this, like this side will be field theory, right-hand side will be classical stuff. Okay, so FT. See if we can make that a little bit thicker. And classical. So as I mentioned, to get to Noether's theorem, it all starts with a Lagrangian. We need to, that's what describes the dynamics of the system. So in classical, you may have seen that it has to do with kinetic and potential energy. So let's forget about potentials for a second. Let's just consider a free particle or an object that's free. The Lagrangian is then just 1/2 m x dot squared in 1 dimension. So it's the kinetic energy. In 3 dimensions, you'd have x dot, y dot, and z dot squareds, and so on. In field theory, it's not necessarily kinetic and potential energies, but we call them kinetic and potential terms. And we also have a free version of the field theory, and the simplest case is called the Klein-Gordon Lagrangian, which is a scalar field that corresponds to a particle that is spin 0, and in general that field can be complex. So for a Klein-Gordon Lagrangian, we have L equals d mu phi squared minus m squared phi squared. So these are the modulus squareds of the fields. In other words, phi squared is equal to phi times phi star. Okay? And the same thing, the derivative of a field is also a field, just like the derivative of a vector should also be a vector and things like that. Okay, awesome. So now let's get into the phrasing of Noether's theorem. Continuous global symmetries lead to conservation laws. Well, what is a continuous global symmetry? A continuous global symmetry means I introduce a parameter to change my degrees of freedom, and I can change it by any arbitrary amount. That's the continuous part. Okay, so as an example, I could have my field, I could do a transformation where my field becomes the original field maybe times a complex phase. So we have e to the minus I times some alpha, where alpha is a real number. Similarly, the conjugate field would would go to the original field times e to the I alpha. Okay? So if this is a symmetry transformation, if this is a continuous symmetry, then the Lagrangian should be left unchanged. Well, if we multiply the complex conjugate squared of the modulus squared of the fields, these exponentials cancel each other, and we're left with the field times the conjugate field. We're left with the original product itself. So that part's left unchanged. The derivatives acting, assuming alpha is just a number, it's not a variable, the derivatives acting don't do anything weird at all. And you can just pull out those exponentials outside of the modulus squared, and they cancel again, and you just get ones. So introducing this complex phase doesn't change the Lagrangian at all. It's left invariant. So that's what we call a continuous symmetry. Now what makes it global is that alpha is constant. That would mean a global symmetry. So continuous global symmetry if alpha is constant. If we let alpha be, say, a function, if alpha was a function of maybe time or space, and things were left unchanged for some reason, that would be a local symmetry. Local. Global because we're changing everything by the same amount. Local meaning we're changing things by different amounts at different points because this weight factor is different at different points. Local symmetries really pop out of gauge theories and quantum field theory, and along with them comes a theory of the gauge fields, which are the particles that mediate the force. So for QCD, if you impose local gauge invariance, you get gluons that fall out of it. If you do the same for QED, you get the photon and so on, the gauge fields. Okay, so similarly for classical mechanics, for fields, multiplying by a complex phase is a little weird, but for classical mechanics, we could do a global symmetry where maybe we have x go to x plus alpha. So it's a translation in the x direction. Well, if we take the time derivative of this, assuming alpha is a constant, then this Lagrangian is left unchanged because the derivative of alpha is 0. So the Lagrangian is completely the same. So that would be an example of another global symmetry. And this has a conservation law that is very familiar to you, and we'll talk about that briefly towards the end. Okay, now let's get into the nitty-gritty of conservation laws from all this. So we're going to start with, if our Lagrangian is left unchanged by the symmetry transformation, it doesn't matter what alpha is. For any value of alpha, the Lagrangian is left unchanged. In other words, the derivative of the Lagrangian with respect to the symmetry parameter is 0, because it doesn't depend on it. Because alpha doesn't depend on any funny variables or anything like that, then the action also picks up that symmetry property. In other words, ds over d alpha is equal to 0. And this is 0 not because we're imposing principle of least action or we're extremizing the action. When you do that, you are changing the Lagrangian. You're manipulating that parameter so that you get the smallest action. Doing this is just a product of saying the action didn't depend on alpha to begin with. Okay, so these are different arguments here. Okay, so let's write this out. This would then be equal to the 4-dimensional integral of the Lagrangian density. And then we're taking the derivative of the Lagrangian density with respect to this parameter. But it's not the Lagrangian that depends on it, it's going to be the fields themselves. So in order to take this derivative, we have to use chain rule. And we have to use that for both the conjugate fields and the derivatives. So rather than writing those all four of those terms, I'm just going to say we're going to sum over the fields. And this is a useful way of writing this because in general for more complicated field theories you can have a whole number of fields. So just saying sum over the fields is much more convenient. So sum over the fields, and then we're going to use chain rule. The derivative of the Lagrangian with respect to the field, let's say the nth field, times that dependence of the field on our symmetry parameter, d alpha. And then we're doing the same with the derivatives of the field, plus dl over d mu phi d mu phi d alpha. Okay? Again, if you're not familiar with tensor notation, this probably looks like a hot mess, but let's go ahead and connect the dots over to how we would phrase this classically. So whenever you see left-hand side number equaling right-hand side, it just means that's how we write those two things classically versus in field theory. Okay? So similarly, if we have ds over d alpha, that would be equal to the four-dimensional integrand measure is replaced with a dt. So it's going to be a dt. Instead of summing over the fields, we're going to be summing over the coordinates and their derivatives. So we have a dl dx, let's call it xn, dx sub n d alpha plus dl dx dot sub n dx dot sub n d alpha. So maybe you would say x1 would be x, x2 would be y, x3 would be z, and so on. Phi 1 would be phi, phi 2 would be phi star, and so on. Okay? Now, this is almost identical to how you would derive the Euler-Lagrange equations. So if you wanted to derive the Euler-Lagrange equations, what you end up doing is you say, I want to factor out this dxn d alpha, but you don't have that over here. You have a dx dot n d alpha. And the way that you can make everything match is you integrate by parts. So if we have the integral of u dv, that's equal to uv at the bounds minus the integral of v du. So if we let u equal dl over dx dot, then du, since everything depends on time, du is equal to ddt dl over dx dot. We'll let dv equal dx dot n d alpha dt. But we can write this a different way. Alpha doesn't depend on time, everything commutes, so we can pull out this time derivative, dx mu d alpha, outside. Let's drag this over a little bit. So this is equal to ddt dx and d alpha dt. So when we take the integral here, v, the integral of the derivative is the argument, is equal to dxn d alpha. Awesome. So varying the action with respect to alpha, ds over d alpha, integral dt, sum over the coordinates. The first term doesn't change at all. dl dxn dxn d alpha minus the integral of v du. So minus, I'm going to put a little parentheses here, d over dt dl over dx dot sub n dx sub n over d alpha. I put the parentheses because the derivative is acting only on the derivative of the Lagrangian. not also on this part here, because x also depends on t, just to make that clear. And then we're adding to that uv evaluated at the bounds plus dl over dx dot n dxn over d alpha at the bounds. But we can throw this term back inside of the integral if we take its derivative, right? The integral of the derivative is the argument. So we can throw this boundary term back inside by taking the derivative. So let's go ahead and make myself a little bit more space for keeping the integral plus d dt acting on the whole thing. Right? And if we take the integral of the derivative, we get the argument on the inside evaluated at the boundaries. So we get back to what we just erased. So the reason I'm putting the parentheses there is because if you don't, it looks superficially like we're adding and subtracting the same term. But these derivatives aren't applied to the same thing. This is applied to only the Lagrangian term. This is applied to both terms. Okay? Okay. And the first two terms, you know, if we were differentiating with respect to just some parameter that our variables depended on and we were trying to extremize the action and setting this derivative equal to 0, that would just give you the Euler-Lagrange equations. But we'll get to that in just a second. So now, how do we translate this? I guess we can call this... Oh, we already... Okay, yeah, so this is 1. We'll call this 2. And how do we say that over here? We'll just do our little translation. So this is equal to the integral dt becomes d4x. Sum over the fields. First term is left unchanged. dl d phi sub n d phi sub n d alpha minus, now things get a little weird, ddt's are replaced with d mu's, dl, sorry, these should be Lagrangian densities, dl dx dots, so that's a time derivative, so that's a derivative with respect to d mu phi. Okay. D phi sub n d alpha. And then our other term plus d mu acting on everything. dl d mu phi sub n times d phi sub n d alpha. Awesome. Cool. So far we've really imposed no physics. Now we're going to impose some physics, which is that our fields are our variables that characterize the motion of our particle. They should satisfy the principle of least action. So now we're saying the action is also extremized from our fields and our variables. Okay? In which case, these terms and these terms are identically 0. And why? Because of the Euler-Lagrange equations. They're equal to each other. So the Euler-Lagrange equations, everybody love everybody. We have d dt dl over dx dot is equal to dl dx, right? That's the Euler-Lagrange equation for the x direction. Similarly, in field theory, we can write it this way. We would have ELE. I guess we can go ahead and call this. So this would have been 2, and this will be 3. We have, what do we have? D mu of dl d mu phi of the nth field is equal to dl d phi sub n. So that's how you would write it in a covariant form, or at least in tensor notation. So this is 3. So if our equations of motion are satisfied, then those two terms are 0. And we already said that varying the action with respect to our symmetry parameter is 0 because it doesn't depend on that. So if the equations of motion are satisfied, then we get ds over d alpha is equal to just this term, d mu dl d mu phi sub n d phi sub n over d alpha. Oh yeah, sum over n. And on the left hand side we get ds over d alpha is equal to sum over n d over dt dl dx dot sub n dxn d alpha. Instead of writing that this whole time, let's give this a name. Let's give the thing in the parentheses a name. It's got one index for mu, so it's going to be a 4 vector, and I'm going to call that j mu. So j mu is defined to be the sum over n of dl d mu phi sub n d phi sub n d alpha. So when we write it this way, we can rewrite this expression, which should be equal to 0 because the variation of the action is equal to 0. We get that for divergence, d mu j mu is equal to 0. Okay. Now, what is this equation? Why do we say that this is like a conservation law? Well, for one, it's a divergence. I mean, there's no source pouring things in here that's not compensated by a sink. But one thing that you could do, like if we say, I mean, these are densities. These are densities here, right? Because we haven't integrated the Lagrangian density. So we could have something like j mu is equal to some density and maybe some current density that I'll call j vector. Then when we apply this derivative term, d mu j mu is equal to d over dt minus gradient dotted into rho and j, which gives you d rho dt minus the divergence of j is equal to 0. And what is that? That's just the continuity equation. Okay, and the continuity equation is exactly the equation that describes the conservation law of some, charge and some current. Okay? So that's where it comes from. That's where, a symmetry leading to a conservation comes from. And here, up here, where we were talking about complex phases, that was just a little example to connect the dots to tether onto throughout this derivation. But nowhere throughout this derivation did we say that this is what the symmetry was. We just said that there was a one-parameter symmetry that the Lagrangian is left invariant under. And if that is the case, then this is the definition of the conserved current. You can then find out specifically what the conserved current is by taking your derivatives of the Lagrangian with respect to your fields and the fields with respect to your symmetry parameter. Now, in a future video, we will do a specific example of what conserved currents, what currents are conserved for specific kinds of symmetries. Namely, we will show that for spatial and temporal symmetries, like symmetries under translations for time and space, the conserved current is the energy momentum tensor, and that is the object of my own personal research. So I'm looking forward to making that video. Now, it turns out that if you go through that with this guy here, if you use this as your symmetry transformation, what ends up being conserved is what we call the charge. Okay, And it's not necessarily a probability that's being conserved, even though that's what we'd like to say because of our familiarity with quantum mechanics, but it has to do with the nature of the Klein-Gordon equation, which makes it so that you can't interpret these things as probability densities, but rather as charges. But we can do that real quick for the classical case. Let's take a look at this transformation here. We have x going to x plus alpha. Let's see what's conserved. So I'm just going to call it j in this case because it's not a vector here, it's just one component thing. And that's going to be on the inside here. So we have a sum over n, dl dx dot sub n, dxn over d alpha. And we want to say, what is our conserved current for this case, for the classical case? Well, the y's and z's are left unchanged. We're not changing those at all. We're only doing a translation in space. X goes to x plus alpha. So when we're doing the summation, two of the three terms that would contribute, the y's and the z's, are just zero because the derivatives are zero because they were never changed in the first place. But if we have x goes to x plus alpha, taking the derivative of x with respect to alpha just gives you 1. So under this spatial translation in the x direction, we get that j is equal to dl dx dot. And if you know your Euler Lagrange equations, we know that that is just the momentum in the x direction. Now you could take my word for that, or you can look up at the Lagrangian. If we take the derivative of L with respect to x dot, power rule brings down that 2, we just get an mx dot. That's momentum. Okay, so what you can deduce, what you can conclude with all this is if we have a symmetry under spatial translations, momentum is our conserved current. Pretty cool. And as I said, in a future video, we'll get into how to extract a specific example of space and time translation invariance, and all of that is combined into one object that is the conserved current, which is the energy momentum tensor. So I hope you all enjoyed this video. I hope you like the new format or presentation of the derivation videos. I'll still use the whiteboard from time to time, but I gotta be honest, it is pretty inconvenient to use, especially with my asthma, because of, I don't know if it's, you know, the markers or whatever that trigger my allergies, but whenever my allergies mess up, then it makes it so that I can't breathe, which is really fun. So having this as an alternative is super nice. Not to mention with my research, you know, I'd say 75% of my calculations are in LaTeX itself, like in an overleaf document, and the other stuff that I can't either do in my head, or I want to check something, or actually just expand and not be lazy. It's been awesome to just be able to go over here, extend the screen so that I can still see what's going on over here, but, you know, do a calculation on the tablet. I've been using the hell out of that. And you can save the tablet little, like what you're writing as a PDF. There's also other softwares that you can use. I've been using Microsoft Whiteboard, but you can use other stuff that apparently lets you convert to text. I haven't tried that though yet, so, you know, I don't know how good that is, at translating math into the text. I don't know. But for what I need it to do, it's been working really well. I'm not a super technical savvy person. I just wanted a tablet that can write well and erase, and I have plenty of space to do calculations with. It may have looked like I was running out of room on this whiteboard, but you can always just zoom out, and then there's more whiteboard there, which is pretty cool. So something that can write well, has an eraser. I am easy to please, aren't I? And has a lot of real estate that you can write on. It's pretty cool. The one issue that I did have that I think I wanted to address, I didn't see anything about it really anywhere else, like Flammable Maths video. Maybe they didn't have this problem. But there's a bunch of cords that you have to plug in from the tablet to your computer, and one of which is a USB. And one thing that I found is that when I would plug the USB into my computer, it would try to draw too much power, and my computer would kind of freak out a bit. So instead I plugged it into a USB hub that had an AC power adapter, and that remedied the problem. Gaomon also just sent me a new cord though, and that remedied the problem as well. So I think it was just the cord. But needless to say, I think it's also worth investing in like a USB hub that is powered itself. That way, if you ever have to charge something, you don't have to worry about how much power it can hold in the first place, so that you're not frying one of the ports. But that was the only issue that I had. Ever since they sent me the new cord, I haven't had any issues. It interfaces really well with Zoom, which is hard not to because you're just sharing your screen and stuff. But it's nice when I have to tutor or if I have to TA, normally I would have to hook this camera up to a cam link, which then I can hook up to my computer to look at what I'm looking at, like as a Skype thing, so that they can look at my whiteboard. And that is super annoying to do. I hate doing that. So with this, it's just as easy as sharing your screen and then you can write, which is loads more convenient. But if you want to hear more about the tablet, go check out Flammable Maths video. Huge thanks to Gaomon for sending me this tablet. You can click links in the description to go check out the tablet for yourself. They also have some specials going on where if you look at the tablet, you can also pick up a free accessory, which could be a screen protector. It could be some fancy Frodo Baggins gloves where he gets his finger cut off. I don't really use those, but they have like fingers that have little holes in them. And I think it's just so that you don't smudge your screen or whatever. But you can pick up extra things like that for free right now, so go check that out. Hope you guys enjoyed the video. Let me know in the comment section if you did, and I'll see you guys there.